All right, hello everyone. I'm glad you could join us. Just wanted to make a quick intro here and let you know that in order to increase the quality and viewer experience, we've pre-recorded a bunch of the content for today, which we'll live stream now. You should be seeing all of the different speakers who will be on today's episode, the first episode of OpenHW TV. Season 1, Episode 1, and we'll introduce all of these speakers over the course of the session. Please enter your questions during the in the Q&A section through the course of the episode, and we'll be back live again at the end of the live stream to open it up to a live Q&A. So thank you for joining us, and here comes the episode. Hello, everyone. Welcome to OpenHW TV. My name is Rick O'Connor, and I'll be the host for today's episode. Today, in fact, marks the first season and episode 1 in what will be a series of streaming webcasts from the OpenHW Group ecosystem. And given that this is our first episode that we are airing, we'll provide a brief overview of the OpenHW Group at the outset of the show today before we move on to the formal part of the agenda. So let's quickly take a look at the outline, and then we'll introduce our guests. So I'll go through an overview of OpenHW Group. We'll follow that with a panel discussion of verification experts from our verification task group. And I'll introduce those gentlemen in a minute. And then we'll have Simon Davidman from Imperis join us to talk about the Imperis RISC-V reference model. As well, we'll follow that with guests from Metrics. Doug Letcher and Amy Sutton will join us and talk about the SystemVerilog simulator that we use in the cloud for Metrics called DSIM. And you'll see that as part of our verification test bench in a moment. Once we've concluded all of the guests, we'll have a viewer Q&A session. So during the course of the webcast, please feel free to note any questions that you might have in the chat window. And then we'll take those questions up at the end of the episode. And you can also come on live to ask your question if that's what you'd like to do. So with that, we'll step into a quick overview of the OpenHW Group if you're new to the organization. OpenHW Group is a nonprofit global organization built specifically for hardware and software designers to collaborate on open source hardware-based IP. In particular, we're focused on processor cores built around RISC-V, the Core 5 family, supporting tools and eval platforms and related IP to those cores. So we have an international footprint with developers from around the world. And beyond just cores, we're really providing an infrastructure for hosting high quality open source hardware IP that can be used in high volume production SoCs. We've got pretty strong support so far from industry and academia, which you'll see in a moment, with more than 49 members and partners worldwide. The first couple of projects that we've got inside OpenHW Group are based on 2 different cores that were developed by the great Pulp platform team under the leadership of Professor Luca Benini from ETH Zurich in Switzerland. It's a world-renowned school, and the team there has been working on RISC-V based systems and architectures for many years. The cores in particular have been known as RISC-V and Ariane. We give them slightly more industrial names, if you will. CV32E4, an embedded class 4-stage deep pipeline embedded core. And then the CV64 is an application processor, 6-stage deep pipe with support for being able to run a full operating system such as Linux. Both of these cores are now part of the OpenHW Group and have been already used extensively in industry and a number of research projects. As you can see here, the cores have been used several times. They're also in production with a handful of customers, but there isn't an open source test bench, verification test bench for these cores that's readily available to make it easy for users to adopt the cores, make modifications, and then still build a verification environment around that. So that's part of what we're up to, building a verification test bench that provides industry quality verification and coverage for these cores to make it easy for adopters to take the cores, modify them, and put them into their own SoCs. We've got a fairly strong ecosystem that's built so far. We only launched the organization 11 months ago, and we're now at 49 members and partners. As you can see here, these are all the corporate members in the organization. And we have quite a representation from system-level companies to SoC companies, tools companies, IP companies, really, really big guys, and medium-sized companies, as well as some smaller guys. So it's a vibrant ecosystem so far and continues to grow. On the research side, we've got a healthy number of universities and more to come who are participating in using these cores in a pedagogical framework inside their schools, as well as the basis for research and innovation projects inside the universities. And we've also got a healthy list of partners. They're supporting us with tools and platforms so that we can develop the open source artifacts and bring those to the ecosystem. So lots of cool stuff going on, and hopefully, if you want to learn more, you'll go to openhardwaregroup.org. That's openhwgroup.org. You can learn more and understand how to join us and participate in the ecosystem. So what are some of the barriers for open source IP? I mean, in the hardware industry, there really isn't a significant IP block that's been used in volume in any production SoC. And why is that? The hardware industry has not benefited from the open source software model that's been in place for decades. And fundamentally, we feel as a result of three key barriers: the quality of the IP, the ecosystem supporting that IP, and then the license models and legal issues surround using the IP. And in today's episode, we're going to focus specifically on the quality of the IP and the verification test bench that we're applying, so that large SoC vendors and systems vendors who are building ASICs have the confidence to be able to take this IP and use it in high volume production SoCs. So with that, I'm going to bring in a panel of experts, and the experts are really the leadership team for our verification task group. So I'd like to welcome Steve Richmond from Silicon Labs, Leo Wang from FutureWay Technologies, and our own Mike Thompson from the engineering staff here at Open Hardware Group. Welcome to the episode, gentlemen.
Hi, good to be here.
Yeah, thanks, Rick.
Thanks, Rick.
So maybe to get us started, Mike, you can do a screen share and walk the audience through our verification test bench for the Core 5 family of RISC-V cores. Okay,
happy to. So our verification environments are built with SystemVerilog following the UVM methodology. You can see there in the center, there is our Core 5 family of cores that can either be a CV32 or 64. I'm going to walk everybody through the verification environment from the left to the right. That's the information flow we've got here. We have programs that are either manually written by people, so somebody sits down and writes a C program or assembler program with the intent of exercising the core, or more than likely, we will get our stimulus from the Google Random Instruction Generator. Whichever way we get the source code, this will run through our GCC tool chain in just the same way that the software team would use it. And that program then gets loaded into the instruction memory where it is executed by the core. This instruction memory has a very interesting set of features. It has some virtual peripherals that do things like dump a signature file at the end of simulation, signal test case pass or failure, or write to the standard out, handle debug, that kind of thing. A real key point to this verification environment is the Imperius reference model. And this Imperius reference model is running exactly the same program that the core is running in lockstep. As the program is executing, we are collecting functional coverage. This functional coverage is either a set of cover groups directly in the environment or a number of assertions bound to the RTL that we reuse from formal verification. Also, as the program is running, we get these asynchronous events coming from either our debug and or our interrupt agent. So as a test program is running, we may or may not be getting debug events. We may or may not be getting interrupts happening. The real key feature to this is the split of stimulus and checking. We check the results as every instruction is retired. So at the end of every instruction, we compare the CSRs, the GPRs, and the program counter, and we print a very nasty error message should there ever be a mismatch. And this whole thing runs from one invocation of the make file. So we've got this one rule that we run that can run virtually any test that we need to run. And that's how this thing goes.
Cool. So Mike, with the step and compare function, I mean, that's pretty, I think that's pretty unique in terms of what we're up to. What happens if it doesn't compare?
Yeah, the short answer is if there's a miscomparison at any time, there is a very nasty error message printed to the log file, and an error count is incremented, which automatically fails the simulation. So we get that indication of a failure right at the time that it happens. The environment also has the ability to display the comparisons that are success, but generally speaking, those are less interesting to verification people. We're always looking for a problem. So anytime there's a miscomparison, either in any of the CSRs, any of the GPRs, any of the program counters, or any time the program counter is looked at, and these things are looked at the end of every instruction, then you get both an error message and an error increment that fails the simulation.
Oh, very good. So, and we'll hear more about the Imperis model that we're comparing against from Simon in a few minutes. So Steve and Leo, from your perspective, I mean, you guys have many years of verification experience. How does the environment that we're building, the open source environment that we're building around this test bench in the OpenHW Group, compare to your experiences in your organizations? Leo, why don't you go first?
Okay. The first thought is the methodology is very similar. I just came off recently from a server project where we have two commercial test generator and as well as one internal one, and each one generator employ like 10 engineers to work on this. And by the way, we also pay a couple of $1 million for all those commercial test generators. And I think it's a open source project that one constraint we're facing is a very limited budget. But I have talked to this with Mike, and the comeback is okay. The beauty of open source is we are able to piggyback on a lot of very good tools provided by companies. For example, like the random test generator from Google and the reference model provided by Imperas. So together we are able to achieve much more with a very much smaller team comparing to a commercial development team.
Thanks. Steve, what's your view?
Yeah, the test bench architecture that we use is something that would be extremely close to if not exactly the same as a test bench architecture that I would use in any IP or processor or any digital block that I would be verifying as part of my corporate life. We use at the OpenHW Group, when we say in industrial strength, we're going to be industrial strength, and we're also going to be in industry standardized as well. We split stimulus from checking. We're relying on the Google instruction generator and the great work that's been done there to generate our stimulus. We're going to be instrumenting a lot of functional coverage to test our testing effectiveness, as well as really utilizing the excellent work, the very high quality Imperius instruction set model to be able to check our design and do that in a fashion that really any verification engineer with any experience should be quite comfortable working in. And with that, we are also in implementation, we're very standards based as well. Anyone who has access to a commercial simulator that can run SystemVerilog with the test bench extensions should be able to replicate all of our results, be able to check us as well, and also hopefully be able to contribute.
So on that front, on the contribution side, Mike, why don't you throw up the workflow slide that we have to show our viewers how how contributors can participate.
Yeah, absolutely. The center of our universe is GitHub. All of our code is up on GitHub, and all of the active contributors working for member companies are all working independently, using their own compute and their own tools. And how we interact is through that GitHub repository, not just for the code, but for tasks that people are working on. So the whole thing kicks off when I will capture a bunch of tasks, a bunch of work that needs to get done. I'll make that information available on GitHub, either by reaching out to an individual contributor at a member company, or just putting the information up there and waiting for someone to pick it up. And as an individual contributor picks up these tasks, they will work on that task on their own infrastructure using their own company's compute and their own company's tools. And there'll be some companies or some contributors at one company working on one task and other contributors at a different company working on another task. This is all happening in parallel. And as contributors believe that they've done the task, and this task can be anything from updating a UVM agent, writing a test case, debugging something, whatever it is, when they feel they're done, they will push that back up to GitHub and issue a pull request. If you use GitLab, that's a merge request. As soon as that happens, that kicks off a regression on the metrics cloud, and everybody in the OpenHW Group can see how that's proceeding. Assuming that's proceeding all right, that regression will pass. I will see that, and then I will merge those results back onto the master branch, and now we've got the feature updated. And this cycle just repeats until all the tasks are done and all the regressions are passing.
Awesome. So Steve, if I'm a new viewer watching this episode and I'm really intrigued by the verification work that we're doing, this test bench just looks super cool, and I want to participate, how do I get involved?
Well, we're extremely visible. As has been mentioned often, we have our GitHub repos. Those are a great place for you to just go look, see what we're doing, see how well the code we are developing has been put together, what it looks like. And if you're ready to contribute, please look us up at the OpenHWGroup.org, the OpenHW Group. We would love to have as many contributors as possible. This is the start of pretty exciting, very novel, very new. Come please join us. We'd love to have you.
If you search for OpenHW Group in Google, the first thing comes up is our website, and then the second is probably just GitHub. It's very easy to find.
Perfect. Okay. Thanks very much for that, gentlemen. Hopefully you've got some time to hang around for the end of the episode, as we'll be having viewer Q&A, and we'd appreciate if you could participate in that. Thanks very much for the discussion during the panel.
Yeah, thanks, Rick.
Thanks, Rick.
Now we're going to move forward and bring Simon Davidman on from Imperis to talk about the Imperis RISC-V reference model. As you heard during the panel discussion just now, our verification test bench is built around the Imperis RISC-V reference model using a step and compare function to validate the cores. So we'll bring Simon Davidman on now to talk more about Imperis and their development history with the RISC-V reference model. Simon, welcome to the episode.
Great. All right. Well, thanks very much. And so it's good to hear Mike and the panel talking about the environment. What I want to do now is to talk a little bit about Imperius and how we fit and how we're working with open hardware on this verification environment. So three little segments, really. A little bit about Imperius and what we've been doing in RISC-V, a little bit about our reference model, and then talking about, and taking a bit further where Mike started, talking about the encapsulation of the model inside of the SystemVerilog test bench. So Imperius. So we believe that nobody designs a chip without simulation. And at Imperius, we founded Imperius with the belief that nobody should develop embedded software without simulation, trying to realize that all embedded products basically were defined by their software. And that's evolved in the last 10, 12 years since we started that, and especially with RISC-V. And what we do is we focus on simulators and tools and debuggers, initially targeting at the software developers, but now much more with RISC-V into the design and the verification. We're 10 years old, self-funded, profitable. Majority of the team, the engineering team, based in the UK. We have people in several other places as well. And our focus really is that we've come from an EDA industry, from simulation, from verification, some people from processor companies, and a lot of embedded experience. In 2016, we went to DAC and saw Krista, the key architect of this from Berkeley, talk about RISC-V. I thought it was an interesting presentation. I chatted to him afterwards, and I wrote one thing in my book, which was academic, as it was an academic thing coming out of Berkeley. Later on, we started getting involved in going to workshops where there was a lot of attendees, 350 at the site of Google's. We joined the foundation, we started building models, we got more and more interest from different customers, not just in the academic space in universities, but actually in real commercial usage. And down in 2019, the revenues that we get related from RISC-V technologies of ours exceeded our ARM related revenue. And up to that point, ARM was the major part of our business. It's still a very large part of it. And we have models of all different technologies across the processors, with some 300 different processor models. But now RISC-V is absolutely a key part of the technology. And in this year, we're seeing people starting to adopt us as the reference in their environments. So in terms of support for RISC-V, one of the first things we did is we took our simulation technology and made a freely available version of it away in a GitHub repository. It got adopted in the RISC-V group's compliance test suite, where it's used there, and pretty much everybody who's building a processor is using it as some form of reference in there. We also have the ability to model custom instructions, and we have methodology of flow like that, because previously we'd worked with people working on Tensilicas and ARC and things like that, which was very much custom processor stuff. We got involved with the Google stream generator, because we saw that generating tests was a key problem, and got involved actually on the functional coverage side of that with them, and added a lot of input to that and stuff there. And then most recently I've got involved in the compare methodologies to help people build better verification test benches, and more on that later. And actually one of the things we did is we were engaged, and we have a couple of customers who have used us for building test environments and test suites for their RTL. And we've built quite a comprehensive suite of verification tests for the vectors, and they're an extremely complex set of instructions and everything. So, we've been involved in RISC-V now for 3-4 years. We're supporting different things. And the key thing that we have is this model that we built, which is a reference model. And it's sort of an envelope model, and it covers the whole of the RISC-V configurations that you can have, whether it's 32-bit or 64-bit, whether it's got floating point or double floating point, whether it has vectors or bit manipulation. And we've got a model which has all of that in, and we update that very regularly as things change. We haven't yet made available the hypervisor and DSP stuff, because that's really still too much in flux. And we have models of a variety of different specific cores, whether they're commercial like Andes or Sci-Fi, or whether they're open source like a low risk or the open hardware stuff. And the sort of highlights of this reference model is it's actually used by people as a reference. Compliance working group use it, customers are using it, whether they're publicly talking about it or whether they actually are using it and don't mention that they use it. A lot of people are using it. So now what I wanted to do was actually just switch a little bit and talk about the encapsulation here. So with the encapsulation, and Mike talked a little bit about that. So we have the reference model, which is one of several hundred that we have built, which covers the whole of the RISC-V. And normally you would run that in your own platforms in C or System C for development, or you could run it as an ISS standalone. But what we've done is we've encapsulated in a SystemVerilog module, where you've got access to all the different registers inside it and the interrupts and the pins. And you have basically DPI, which is a SystemVerilog interface technology for allowing C to access SystemVerilog and vice versa. We basically can take the C of our model and present into the SystemVerilog world, basically tasks and functions that can be used in that and simulated. And so you can step it, you can read and write values and registers. And what we've done is we've taken that as an encapsulated model and put it available in the test bench so that you can step it, as Mike showed the OpenHW one. This is one that we provide as an example in one of our products. And it's exactly what Mike was saying. You load the program into memory, you step it along, and you compare the results in it. And what I was just going to do is here on my machine, I actually have an installation of the Open Hardware Test Bench. And what I was going to do is just run a simple example. So this is an encapsulation of the UVM SystemVerilog Test Bench, encapsulating the Imperius Golden Reference Model and running actually the dry stones. And I just installed this from the GitHub, from the Open Hardware repository, and there it's running. And at every instruction retirement, it's comparing the reference to the RTL. And you can see, nice big banner, it's passed, it's gone through. There's a lot of data and statistics and the whole suite of these. And just for completeness, just to show one of the questions that Mike was asked by Rick about what happens when something goes wrong. So here we're running some of the compliance tests, and actually one of them we've changed, and you can see them going past. One of them we've changed to just, I think it's one of the loads, so it accesses some illegal memory or something like that. And you'll see at some point, it detects it, it will stop the test process, and it's pretty obvious that something's happened there, right? So you get the failure. So that was really just a quick demonstration of it running. And now just to sort of conclude my segment here, this show is really, so we've been working with the Open Hardware Group, and the key thing is to ensure that the cores is delivered at the highest quality, and they've gone through the maximum verification you can. Our focus is dynamic verification. And this is using the state of the art in terms of commercial flows and industry standard Verilog tools and things. And what it means is that as you adopt Open Hardware Group cores, you get the same, you can use these same approaches if you extend and modify them. And I believe that a key value, at Imperius, we believe a key value in this Open Hardware Group deliverable is the verification environment that comes with it. And you download it and run, and as I showed, it running just there. So that's my presentation, Rick.
Thanks, Simon. Appreciate your insights, and thank you for your support.
Thank you.
Okay, moving right along, we're going to bring Doug Letcher and Amy Sutton on from Metrics. The other key element of our verification test bench is the simulator that we run on, and it's in the cloud. That's the DSIM simulator from Metrics, and it is a commercial grade SystemVerilog simulator where we run all of our regressions and tests for the Core 5 family of RISC-V cores. Welcome to the show, Doug and Amy.
Thanks, Rick, for the intro. And as Rick said, we're here representing Metrics, which is a cloud-based EDA solution for running large sets of simulation, SystemVerilog simulation jobs in the cloud. And particularly useful to a group like Open Hardware is that this gives you an industrial strength simulation solution that is equivalent of what you would have maybe at some of the companies where you all work outside of Open Hardware, and that allows you to have a collaborative work environment as a group within the open source context. And I know that myself and the people at Metrics are big supporters of open source software and now open source hardware with Open Hardware. So we're very happy to be able to provide this type of solution to the group. And the key features of what you'll see here in the demo upcoming from Metrics are related around continuous integration, collaborative development, simulation capacity that provides everything you need to run your simulation, SystemVerilog simulations out of the box with an efficient workflow, everything you need to get to coverage closure, and particularly the ability to provide remote support because we are a cloud native type of solution. So with that, I will hand it off here to my colleague Amy to run through our demo, and let's go ahead, Amy.
Thanks, Doug. I'm going to share my screen to give everyone a look at what Open Hardware members see when they log into Metrics. So this is our dashboard screen, and this is actually live results for the CV32 core, which is under development at Open Hardware and is in the process of the verification and eventually will be into coverage closure. So the charts that you see, the first one shows the number of passed versus the number of total tests. The second one shows functional coverage, and the third one shows assertion coverage. When you see a point in the graph where the number of total tests goes to 0, that's a point where there was a compile or a build failure. And that type of thing is expected, especially when people are doing continuous integration and constantly testing their changes. Sometimes those changes don't compile. Metrics has all the tools that you need to debug those failures. Functional coverage. So eventually you'll start to see a trend where coverage increases higher and approaches 100%. These charts just give an overview of how your project is doing over time, and soon this kind of information will be made publicly available even outside open hardware. So let me click on results so that you can see the information that we collect and present for every regression or batch simulation run that's done on metrics. So the top row is the most recent batch simulation. This is the name of the regression. You can see the Git branch it was run against, the commit hash, the author of that commit, and the person who actually started this regression, statistics about time and duration, and then the number of tests that are either pending, running, passed, failed, or incomplete. As well, we have statistics for merged results for functional and assertion coverage. So Doug mentioned that coverage features are part of the metrics solution. Coverage closure is a very important part of industrial quality verification that Mike was talking about earlier. And this is a task that metrics completely offloads from our users. Whenever there's functional coverage code in your SystemVerilog, will automatically merge the results of all your simulations and present the merged value here. So in this continuous integration workflow that we have set up for open hardware, the act of committing changes will kick off one of these sanity regressions, and these can be used by developers on an ongoing basis to make sure their code is of good quality. And it can be also used by people who are approving pull requests for the same thing to make sure that the code is of industrial quality. So let me show you what some of these results look like. So here's a list of all the tests. You can see the first one has failed. It's indicated by the X. And here we've got some debug tools that people at Open Hardware can use to start to debug these results. And the great thing about our debug tools is they are available anywhere you have a web browser. So we have a log viewer, which opens to the end of the log file where you can quickly see your pass-fail status. It has a database index search capability where you can search either using a regular expression or a regular token and quickly look at failures. We have access to historical results so that you can look at past logs, and you can open multiple logs at the same time in case you want to compare two simulations or look for common failures. The other tool we have is a waveform viewer, and this we believe is the first browser-based waveform viewer in existence. Opening your waves is as easy as clicking on the link that I just did, and they'll open in a separate tab for you. You can either choose to add signals using the traditional method by going through the hierarchy, or to open a saved session or your most recent session. So I'll click on this link to open a saved session, and this takes you to the view of the waveform at the time that I saved this session. So this is a great feature for collaborative development because it's easy to share these sessions among users. You can either send the link by email, or you can embed the link in a GitHub issue. Here you can add cursors showing important times and give them a meaningful name, add a description of the issue, and also include links here as well. And when your colleague clicks on that link, they'll get this exact same view of the waves that you were looking at. The other thing I should mention is that The performance of our waveform viewer is very good because we fetch data on demand. So we can manage large number of signals, and we have made this easy to use for people who are used to working with EDA tools interactively. Okay, the last thing I'm going to show you is our coverage viewer. So by clicking on the coverage result, that opens the coverage browser. You can navigate through your test bench hierarchy to look at cover groups. And because there's a lot of data here, we have a filtering capability where you can add filters to help you focus on the results that need most attention. So if I only want to see cover groups whose coverage is less than 50%, I can add a filter and the view will change. And viewing the source code for this coverage is as simple as just clicking the link next to it, and it will open the cover group in GitLab. And it's important to note that it opens to the hash or commit of this code that is associated with this regression. So you're always looking at the actual code that was used to generate this coverage report. We also have a feature called Merge Sources, which should help you with coverage closure. This is essentially a test ranking view, ranking these simulations by their contribution to functional coverage. So right now, there are only a small number of tests. Coverage numbers are low, but this will change over time. And you may start to see some redundant simulations at the end, which are not adding to your coverage goals. So this view helps you to optimize your regression set, focus on the tests that are getting you the most coverage contribution, and then just add the ones that are needed to cover the holes. So with each regression, you can also see the rank associated with each particular test. And as I mentioned, there's a small set of tests right now. Development is ongoing, and Metrics is really happy to support the development efforts of the OpenHW Group. And we think that the distributed nature of our platform is a great fit for the goals of the OpenHW Group, and the tools that we provide will help them to achieve their industrial quality verification. So thanks for giving us the opportunity to present, Rick. I'll send it back to you.
Thanks very much. Appreciate your support. And thanks a bunch to the Metrics team for helping us get our test bench up and running. With that, that wraps up the scheduled content for the episode today. We're now going to open it up to Q&A, and several questions have come in over the chat window. We'll go to those, as well as open up some mics. So just raise your hand if you want to ask a question live, and we'll patch you in and you can ask your question. Great. So we have actually a number of questions in the Q&A panel. I want to make sure that all of the speakers unmute their mics so that you can answer these questions when you're ready to go. And I'm just going to read out the questions, and then you guys can jump in with answers as you see fit. So one of the first questions right off the bat we had at the beginning of the session was, how would someone add an accelerator and verify the extended core with this verification system? So to reframe it a little bit, someone say wants to take one of the cores, bolt a custom accelerator on the side, then what do they do with our verification environment?
I can take that.
Who wants to go first?
I can take that, Rick, if hopefully my mic is unmuted.
We can hear you.
Okay, good. So the Core 5 verification environments have been specifically architected with this reuse in mind. So we're not building one test bench for each core that we do. We have a number of cores that are in development right now, and the idea is to have a single verification environment. And the way that we handle the differences between these cores is very much the way that I think we would address the issue if someone wanted to come in and bolt in their own accelerator onto their core. And that is all of the low-level details of the core are kept down at the bottom in the test bench module. So if you have, for example, specific interfaces for interrupts or a specific memory controller interface that you need to connect to, that is handled down at the lowest levels, and that is difficult to customize. So that is difficult to abstract. So that there's a certain level of customization that has to go on there. On top of that, though, is where the UVM environment comes in, and that's where the abstraction is. And so that abstract UVM environment is able to deal with any one of those low-level test benches. You may or may not need some additional tests to deal with your accelerator, so you'd have to add those tests in. But we have a way to do that if that is completely independent of the test case, or sorry, of the test bench. So it's really done with keeping the low-level details at the lowest level of the test bench, doing your customization there, and then that allows you to exploit all the abstract components at the top in the UVM layer.
Thanks, Mike. Anybody else? Steve, Leo, you want to comment on that or move to the next question?
I can add a little bit. So like Mike said, because you need additional input to access the accelerator just by using our default test, it's not going to magically send instruction to the accelerator. So that definitely there need to be some work. And also you want to consider, is the accelerator going to be open source? In that case, you might want to contribute, and that's easier to work with for everybody. If it's not open source, then we have to consider how to package it, treat it as potentially you can provide as a interface as is now, and then that way the community can also help you integrate.
Awesome. All right, so a couple of questions came in about what's open sourced and what's not, and membership requirements and so on. So I'll kind of group them all together, and I'll answer that and then we'll move on. So the OpenHW Group is a completely open source organization. So everything that we develop is freely available to anyone. You don't need to be a member of the OpenHW Group. Everything that we do is up on GitHub. So like Leo said at the outset, if you just Google OpenHW Group, you'll find all kinds of links, obviously, to our site as well as to our GitHub repo. One of the main focuses for the organization, however, is to make sure that what we do stitches into commercial tools, right? Because large volume SoC companies go to production with existing commercial tool chains that they use to produce known good silicon, right? When they're investing millions of dollars in mask sets for deep submicron technology, messing around with the tool chain is a fireable offense, right? You basically, you want to leverage the existing tool flow. There's other organizations that are working on some open source tools, and that's fine. People can look at those and use those. But the intent is that everything that we have, we're proving to run on the existing commercial SystemVerilog simulators. Our regressions run on the metrics environment, and there's members working with the big three: Mentor, Cadence, and Synopsys tools, including us working with Cadence tools as well to validate everything in commercial tool flow. So go to GitHub. You'll see the Core 5 verification test bench. It's a pretty active environment. Just look for OpenHW Group as our account, and you can start participating. If you want to join, if you want to actually drive the priority of the projects, that's the region to join. So membership is if you will, the group that decides what we work on, with what priority, what the focus is, and so on. If you simply want to use the artifacts as they come out and are ready for prime time, you can just get that stuff from GitHub and away you go. Clearly open source projects thrive when people participate and engage, If everybody just takes and nobody gives, then the stuff sort of goes away. But Simon, you got a comment?
Yeah, so Rick, I wanted to comment, and I think the key thing that you said there and Mike said there is that what Open Hardware is doing, it's providing extremely high quality RTL cores, which will be extremely well verified. And that's why, for example, in Imperius, we're making available our sort of reference model, and Metrics are providing simulation technology so that there will be millions and millions of cycles done in the cloud out there by Mike and his team on the verification of it, so that anybody who uses the core just by downloading it from the GitHub gets an extremely well verified core. Now, if they want to extend it or run the verification themselves, then they've got to use the commercial tools that the verification environment is based on around SystemVerilog and the complexities and things like that. But that's only if they want to extend it. If they just want to make use of it off the bat, then they can just download and run it, and they do not need to use all this verification environment. But if they do want to do the verification themselves, then yeah, it's based on commercial tools.
Exactly. All right, another couple of questions here related to the cores and modifications. I'm going to group a couple of them together. Let's see, I'm just scrolling through some of this. Give me a second. Oh yeah, so I'll read two questions that are pseudo related. Is it possible to implement data and instruction prefetch in the cores that will be verified in this environment? So hold on for that for a second. And then there's another one here. Does the approach that Mike described support tightly coupled functional units inside the processor pipeline, such as accelerators? Right, so it's kind of getting at some of the same things that we've been talking about, but maybe you guys can comment on those questions.
I'll comment on the big one, which is the use of accelerators. So there's nothing in our environment that is preventing us from handling a core that has accelerators inside it. When you bring in new functionality like that, there's really two issues that come into play. One is, are you able to continue verifying the device even though you've made an addition to it? And that's the easy one, because we'll be able to handle that. The verification environment that's in place will just run, and that shouldn't be a problem. But if you're going to introduce new functionality, there's work that you need to do there. So we always start with, first of all, writing a verification plan. These verification plans, by the way, are up on GitHub, just like everything else we do. And that verification plan would describe the features that you need to verify. It will also tell you if you need to add additional functionality to your verification environment, and whether you need to write some additional test cases. So there's no free lunch here. We can handle the addition of these capabilities to the device under test. But if you add these new capabilities to the device under test, you have to add similar capability to the verification environment to make sure that they're verified. I hope that answered the question.
Well, if it didn't, keep asking the question differently in the Q&A window, and we'll get to it again. So there's a couple of questions that have come in specifically for Metrics and for Imperius, so we'll get to those now. So Doug and Amy, the question here is, does the RTL and verification code need to be inside GitHub, or does your environment support internal company repositories?
Thanks, Rick. I'll take that one. No, the RTL doesn't have to be inside GitHub. In fact, GitHub's obviously very popular in the open source world and being used by Open Hardware. So we extended in that direction, partly as an effort to support the Open Hardware Group and other open source project groups. But our commercial customers tend to prefer either internal Git repositories or legacy other source control repositories, or Metrics actually ourselves can host a private, secure Git repository for commercial customers as well.
Perfect. And then Simon, this is your favorite question. If I didn't know better, I'd say you paid somebody to ask it. And it's, do we really need an ISS, or do we have to have an instruction set simulator to test the cores, or is there another approach we can use?
Yeah, I mean, actually, yeah, there's lots of approaches you can use. You can get a $500,000 formal tool. You can run random tests, but the problem is you don't know whether they've generated good results. And the challenge always with all testing is, how do you know that the device you've built does what you expect it to do? So somehow, somewhere, you've got to be comparing your RTL with something, whether it's formal and all the complexities of that, or you have to have a reference, or you have to write extremely careful directed tests. But I think, the last 25 years of hardware DV has told us that you need many different approaches to verification. And from a dynamic simulation point of view, you basically do directed tests where each test carefully checks what's going on, or you use a reference and compare it. And you can use a reference in multiple ways. And, working with the RISC-V compliance group, their approach there is that they use a reference model to generate a signature, and then they run the RTL to create that signature and then compare the signature after the effect. You look at the way that the Google and all the stream generators work is, again, they do a similar thing. They will generate lots of instructions and then have to compare them against a reference. So those are two approaches. The other is carefully directed tests. So the question, do you really need a reference ISS? Well, history's told us that the best verification does use a reference simulation. And there are two ways to use it: post sort of trace compare, or step and compare, which is being used in the open hardware test bench, the UVM test bench here. And that is really the gold standard in simulation today for verification, because it means you can use any generator you like, throw any test, compliance test, anything you like into it. And for every instruction, you're comparing all the results inside the state of one model and the other, the RTL and the reference. And it means you can get far better coverage and much better results with your generation of tests. But one of the key things, which is really very interesting, is that most tests, when most devices are almost finished, a lot of the bugs tend to be found with things like formal in the interaction of asynchronous things like in and out of debug modes, exceptions. And the key thing about this UVM test bench in open hardware is it allows you to run in lockstep, which means you can do asynchronous events and run randomness, random streams, and asynchronous events, switching modes, and compare at every instruction. And so, from my point of view, unless you're using really expensive formal technologies and all of the efforts in that, then you absolutely have to have a user reference simulator.
Yeah, if you don't mind, Simon, I'll jump in and just reinforce that point. Every simulation environment, doesn't matter how it's implemented, at some point has a reference model in it. And you can put that reference model in an ISS, as we've done working with Imperius, or you can put that reference model in a collection of 1,000 test cases. But sooner or later, you're going to have a reference model. It's a lot easier to maintain if it's in one place. It'll run a lot faster, and you won't be constantly editing test cases every time you write a test. And just a little experience here. This really happened in the last several weeks as we were integrating the ISS as a reference model in our environment. We were running test cases that had been previously developed that had a pass-fail indication. On their own. These tests were integrated, running, passing. As we integrated them with the Imperius reference model, we popped 3 bugs by doing that. 1 was in the test bench, 2 in the RTL. So we had previously existing tests that were previously passing. Everybody thought things were going great. We bring in the reference model and pow, RTL bugs fall out. We would have missed those completely without the reference model.
Great. Slightly different question from one of the viewers around the recent announcement that the Pulp team and that we made regarding Ariane, the 64-bit core called the CVA6 application processor, 6-stage deep. So as with the 32-bit core that we have, the RISC-V core, these began life at ETH Zurich under the leadership of Luca Benini. And the intent from the beginning, in fact, the catalyst that got OpenHW Group started was to build a professional industry quality verification environment around these cores in an open source environment. That's how OpenHW Group got started about 11 months ago. So the 32-bit core was the initial focus with the intent that we would always be the ultimate home for the 64-bit core, Ariane. So that repo transfer, so it's not a fork, it's not a clone. The repo no longer exists in the Pulp platform GitHub environment. The whole thing has been transferred to the OpenHW Group for the 64-bit core. And there's active work amongst the membership now, and what actually has been for quite a while. We've just been working into the repo under the Pulp platform account, but now that environment is transferred to OpenHW Group. So the question here was, are there already entities, companies, foundations, people who are committed to contributing code? So the short answer is yes, and just start hanging out in our GitHub environment and you'll see what's going on. Let's see. We'll stay here as long as people want to listen to us answer questions. So if people have more questions coming in, please just go ahead and put them up in the chat box. I've been sort of throwing a few of them together. So if you feel like your question hasn't been answered, feel free to ask it again, and we'll do our best to answer it. Okay, I think. So just to give you guys an idea or flavor of what this was like, we had over 100 registrations for the event, and I think the audience participation peaked out above 60. So a bunch of good number of people logged in. I think total of 14, 15 questions were typed in here. And I think I'm going to just take a quick look at some of the other questions that we had that were asked beforehand and see if there's anything that we haven't covered. No, I think we've covered everything. So we want to respect your time. Want you to know that the next session, so we're going to do this every month, third Thursday of the month, will be a new episode of OpenHW TV. So episode number 2, coming up in July, is going to be focused on the cores. So the Core 5 family of open source RISC-V cores, sort of a medium to deepish dive into the architecture of the cores, as well as the overall status of where they are from a verification standpoint and the roadmap of what that looks like. So if you're interested in the cores themselves, make sure you mark that in your calendar. The third Thursday, I think it's the 16th of July, if I've got the date right. But there'll be plenty of notice on our social media channels and email groups about the event. So that wraps up our episode for today. I'm glad you were able to join us. I hope you found it informative, and we are always interested in your feedback. So please reach out to us at openhrdwaregroup.org or on our GitHub repos or any of our social media channels. And thanks very much to all the panelists who participated. And wherever your day is today, I hope you have a good one. Bye for now.